Okay, so in this video, we will find the volume of the solid of revolution obtained by revolving this region about the vertical line x equals -1. Now, if you remember in our previous two videos, we used the exact same region, right? The region in the first quadrant of the xy plane, bounded by the curves y equals root of x, the y-axis, and the horizontal line y equals 2. But in those two cases, we used the y-axis as our axis of revolution. Now we're using instead the vertical line x equals -1 as the new axis of revolution. And again, we will find the volume of this solid in two different ways. In this video, we will use a horizontal set of rectangles. In the next video, we'll use a vertical set of rectangles. So let's try and draw the full solid of revolution. So you can picture revolving this region about the vertical line x equals -1, and what it will generate is essentially the same solid that we had in the previous two videos, but there'll be a cylindrical hole in the middle. So it's going to look something like this. So you can see this is our region in the xy plane, right? This is the y-axis. The top is given by the horizontal line y equals 2, and the outer boundary here is root of x. And again, the axis of revolution goes through the center of your solid, and you can imagine now more easily as you revolve this region about the axis of revolution, you get this really nice solid, but then there's the cylindrical hole in the middle, created by, of course, the gap between the axis of revolution and the region. So once again, a very complex but very nice solid of revolution. And we're asking, what is the volume of this solid? Well, let's see. So here we'll take a set of horizontal rectangles. Positioned along the y-axis. Well, first, what is the width of our rectangle? This is an infinitesimal change along y, so the width is, of course, dy. And we ask now, and you can look at the picture, instead of looking at the solid obtained by revolving the entire region in the xy plane, we will revolve a little rectangle inside the region, namely this one. And you ask, well, what solid will you obtain by revolving this rectangle about the axis of revolution? Well, if you think of it, the rectangle is perpendicular to the axis of revolution. So as you revolve this rectangle, you'll obtain a disk, but as the rectangle is away from the axis, it will be a disk where the inside is missing, so it will be a washer. Again, the center of your washer is, of course, the axis of revolution. And we can see the rectangle that generates this washer. So there it is, right? So as you take the small horizontal rectangle and you revolve it about the vertical axis of revolution, you obtain a washer. So let us first find the volume of this washer, and then from this we know we can easily obtain the total volume of the solid using integration. Okay, well, what do we need? We need the surface area of our washer and the thickness, the width. Well, this is clearly the width of the rectangle, So the thickness of our washer is simply dy. And if you remember, to find the area of this portion, we need to find the area of the larger circle minus the area of the smaller circle, so we need our two radii. So we need the small radius, lowercase r, and we need the larger radius, uppercase r. Well, let's try and measure both. And again, because we have a dy, everything we measure must be a function of y. Well, let's look at our small radius first. The small radius goes from the center of the washer to this point. But if you look at this section right here, we go from the center of the washer to the first time we touched a rectangle. So we can look at the corresponding length in the xy plane. The center of the washer, of course, is the axis of revolution. So we go from the axis to the first time we touched a rectangle. So we have to go from here to here. So this line segment is the smaller radius. Well, let me extend over here. Well, let me include the small radius here so you can clearly see it. So that is your small radius. Let's compute it, right? From the axis to the first time we touched a rectangle, from the axis to the first time we touched a rectangle. Well, it is a line segment along the x-axis, so we need the bigger x value and the smaller x value. Well, at the right-hand point, we are always along the y-axis, and here x equals 0. This is our larger x value, always constant. The smaller x value here is -1. And of course, now that we have the larger x value and the smaller x value, to find the length of the segment, we take the larger value and we subtract from it the smaller x value. But 0 minus -1 is of course simply +1. So we have a constant inner radius of 1. And this is clear again from the picture, as the inside of our solid here is a vertical line. So it gives us a cylinder with a constant radius of 1. What about the larger radius? Well, we go from the center again to, if you move the ray here, to the other end point of the rectangle. So with the small radius, we go from here and we stop to the first end point. With the larger radius, we go to the other end point. So we'll go from here all the way up to here. And that is the larger radius. Well, again, it is a horizontal segment along the x-axis, so we need the larger x value and the smaller x value. We already have the smaller x value, it is -1. What is the larger x value? Well, at this point we are on the curve y equals root of x. We want the x value, so square both sides, and so x will be y squared. And now we're good to go. The length of this segment is the larger radius. The bigger x value is y squared, minus the smaller x value, which is -1. So in the end, the larger radius is y squared plus 1. And now we're good to go, right? So you say, okay, well, what's the volume of our little washer? If you remember, we need the area of this portion times the thickness. To find the area of this outer rim, we take the area of the larger circle, so pi uppercase r squared. But now this includes all of this. We have to remove the area of the smaller circle, minus pi lowercase r squared. That is the area of the outer rim, times the thickness dy gives us the volume of this infinitesimal washer. Of course, we can factor pi on the left. So all we have is pi larger radius squared minus smaller radius squared dy. And now we're essentially done, right? You say, okay, we know the volume that is of the infinitesimal washer is this that is being generated by an infinitesimal horizontal rectangle. If you look now at the total solid revolution, this little rectangle cuts a little piece of the region, and as you revolve this little rectangle, you get this little washer within the full solid revolution. Or you could imagine it would give you a slice like this. It would go around, so you're cutting through a little slice of the full solid. You get an infinitesimal washer whose volume equals this. And of course, to get the total volume of the solid, we must add the volume of all of these little slices of all of these infinitesimal washers. Of course, the action of adding is the same as summing. Summing is integrating. So now we're good to go. So the total volume will be summing the volume of each little washer, each little cross-section of the full solid. Of course, now we'll replace uppercase R was y squared plus 1, so we square this, minus lowercase r squared, but if you square 1, you get 1, so it's just 1, times dy, and where do we begin our summation, and where do we end? Well, again, the little rectangles generate the washers, so if you go backwards, we need to add, we need to sum the volume of our little washers within the full solid, but they are generated by the rectangles, so the washers begin where the rectangles begin, and they end where the rectangles end. Again, this is dy, so we have to look at the end and starting point of the rectangles along the y-axis, and the rectangles begin at 0, and they go all the way up to y equals 2, so we have to integrate from 0 to 2. So there you go. So now we're summing all the little infinitesimal washers that make up the full solid, and of course this will give us the total volume. And now we can simply use the fundamental theorem of calculus. First thing, we can factor pi outside, being a constant multiple. We can't integrate this square as it is, so we'll square it, multiply, and then we'll have a simple polynomial, and we can use the power rule. So if you square this, you'll get y to the 4 plus 2y squared, and here I'll be slick, plus 1, but we're subtracting 1, so this will cancel. So we're left with this. Now we can apply the power rule. To find our antiderivative, we'll get y to the 5 over 5 plus y cubed over 3, so we'll have 2/3 y cubed. And we must evaluate as y goes from 0 to 2, pi times. So we evaluate our antiderivative when y is 2. 2 to the 5 is 32 over 5. Plus 2/3. Well, 2 cubed is 8. 2 times 8 is 16, so plus 16 over 3. Minus pi times the antiderivative at 0, but the antiderivative at 0 is equal to 0. So we subtract nothing, so that is our final answer. Of course, you can simplify a little bit. We want to have a common fraction, so cross multiply. 32 times 3 will give you 96, plus 5 times 16 is 80, over 3 times 5 is 15. 90 plus 80 is 170, plus 6, 176 over 15. So it's 176 over 15 pi. And that's it. So, our conclusion is, if we consider the region in the first quadrant of the xy plane, bounded by the curves y equals root of x, the y-axis, and y equals 2, and we revolve this region by the vertical line x equals -1, we obtain a very interesting solid of revolution, and its volume is exactly equal to 176 over 15 pi units cubed. And that's it. So in our next video, we will find the volume of the same solid of revolution, but instead of using horizontal rectangles, we'll use vertical rectangles.